Hi, everyone. Welcome to the third and I think the last webinar in this series of uh, Decentralized AI and Privacy Preserving AI webinars. Today we have Andrew Trask with us from the Open Mind community. Andrew is also doing his PhD at Oxford. And we have our host Nicholas from Meetup AI who will be helping with the moderation. So, Andrew, maybe you can tell us a little bit about your journey and open mind, and then towards the, let's say, second part of the conversation, we can talk more about uh, the efforts that you guys are doing around COVID-19.
Yeah, thanks for having me on. Good to see you both. So for those of you who aren't aware, OpenMind is an open source community focusing on lowering the barrier to entry to privacy preserving tools, like privacy preserving machine learning tools. And we do this through two main ways. So one is sort of free education and community and tutorials and these kinds of things. And the other is free open source code. So we got started about 3 or so years ago. And this was really around a realization that even though there are lots of disparate communities working on privacy, say, there's a group in kind of the cryptography space and folks in the machine learning space, folks in the legal space and policy space, folks in some like app development, like how to do privacy preserving apps, that from a tech stack standpoint, there wasn't a lot bringing all these together into kind of one cohesive space. If you wanted to do, say, homomorphic encryption and deep learning, like train an encrypted deep learning network, then you had to basically go and find, some C++ blob somewhere that was doing homomorphic encryption, possibly at like the bit level, and then cobble together something and roll your own neural network using, individual integer operations and, roll your own back propagation and like sort of all the little tools to actually get it to work end to end, as opposed to, spinning up a deep learning framework and just saying, hey, do it on encrypted data, right? And so I think really there's a wide variety of privacy preserving use cases that are like this, where people have solved really hard problems and even made those solutions available. But it's really an ensemble of a lot of these solutions that you need together in order to be able to deliver end-to-end privacy preserving use cases in society. And so it's our hope that through education and free software, we can empower people to be able to deploy these kinds of privacy preserving use cases, even if they don't without them having us become like a super crazy expert to roll everything by hand by themselves. So yeah, that's sort of who we are and where we came from. Oh, I think I lost your audio for some reason.
I was on mute. Sorry, I forgot to unmute myself. So
No
I wanted to ask more specifically about, let's say, would you say the topology of OpenMind, like the set of tools that you've built, and the ones that you think would be more relevant for, beginners to start with.
So it depends on where they're coming from in terms of background. So if you are, say, a web developer and you've worked with sort of web-based technologies, then one of the best places to start was actually one of our newer projects, which is COVID-related, is to look into some of the JavaScript projects around how you can work with data while it's encrypted inside of your web app. So I think probably one of the best examples of this is this task called private set intersection. So it's sort of a group of tasks, and a lot of really interesting problems can be formed as a private set intersection problem. So if you learn how to do this in the context of your app, then it provides you a wide array of potential use cases. So private set intersection sort of goes like this. Let's say that you have a set of objects and I have a set of objects, and we want to be able to figure out if either of our groups are the same, right? So maybe you have like a list of names and I have a list of names. We want to figure out if there are any overlap. But I don't want to send you my set and you don't want to send me your set, and we don't want to give it to someone else to figure out the list of names. We want to do something together where we can figure out what we have in common without necessarily sending it directly to each other. And there's a JavaScript library that you can go check out. That's happening in the OpenMind community. That's just, I think it's psi.js is the current name. And it seeks to make this possible, where it's possible for sort of two users. This could be a server and an app, or a server and a client, or this could be two clients. This could be two servers, like two Node.js servers, that can perform this calculation in a way that you can tell whether two sets of things are the same. And I guess, I don't know if we want to pivot already to the second half, we'll talk about a bit and how this actually can be quite useful for apps such as like contact tracing and these kinds of things to help preserve privacy. But it's a really good general purpose tool. It's the kind of thing where there's lots of under the hood approaches that people are doing to optimize this and make it really fast. But as far as like a good place to start, if you're a JavaScript developer, then like that would be a good place to start. Now, if you're a machine learning person, there are other sets of tools you could start with. So I would recommend jumping into a tool that we're working on called PySift. That if you're familiar with deep learning frameworks like PyTorch and TensorFlow, you can say take a PyTorch tensor and basically transform it into an encrypted state and still use PyTorch on top of it, right? So I can take a neural network and I can encrypt all the weights and still do training or prediction, or I can take a data set and put into an encrypted state and still train and predict on it. And so, yeah, I think really just playing around with some of the tutorials is probably the best place to get started. So in PySift, in the GitHub repository, which I guess I can drop a link to real quick, you'll find a folder called examples. Inside that examples,
someone shared it actually.
Oh, you shared already? Oh, perfect.
Yeah. I think we have a lot of people who are somewhat familiar with OpenMind already. So I think the flow right now is great. So if we could talk about different developers, machine learning people who are maybe just familiar with cryptography, but then not machine learning, and the normal Web2 programmers, what are the entry points for them?
Yeah, so if you're familiar with cryptography and want to participate in OpenMind, it's my great hope that we are putting together libraries in such a way where cryptographers can focus on solving hard cryptography problems. And when they do so, that sort of the rest of the infrastructure can automatically inherit their solutions and find them into deployments really quickly. So for example, like we have sort of high-level private set intersection libraries, right? And so if you have a new, faster approach to private set intersection, like I think we just added one that's inspired by the new one based on homomorphic encryption or partially homomorphic encryption, then the people who are sort of using the high-level interface of private set intersection,
they just got an upgrade.
They did, yeah. They just, but they don't necessarily have to worry about the low-level stuff. If you improve, with a better algorithm, with a published paper or something like that, all of a sudden everyone does a version update, and all their private set intersection around the world is faster and more secure and all these kinds of things. And your invention has found, hundreds, if not thousands of, maybe someday millions of users, but without having to necessarily go and do all the enterprise deployments and all this kind of stuff. You can just focus on solving really interesting and hard problems. Same thing on the deep learning side. So in PySift, we try to make it so that all of our encryption algorithms are packaged as a tensor type. So that's sort of one of the I guess design principles of the SIFT ecosystem, is that sort of everything is a tensor. So because lots of people know how to use tensors to do interesting things like deep learning and machine learning, but under the hood, when I add two tensors together, it can execute some sort of protocol that does a zero knowledge proof verification of the addition, or uses homomorphic encryption to actually perform it, or secure multi-party computation to perform it, or perhaps it even just keeps track of like your differential privacy leakage if you were to publish the result, like this kind of thing. So because everything on the deep learning side is baked underneath these tensors, it gives cryptographers sort of a place to go to work on really cool cryptography problems that have the potential to be automatically inherited by a much wider ecosystem of applications that are consuming them.
Could you maybe tell us who's responsible at OpenMind, or if there's a team that people could directly go to?
Yeah, sure. So there is a wide variety of development teams and community teams that do a lot of great stuff. And just for context on how teams work inside of OpenMind, so they're commonly a mix of people who are volunteers and who are sponsored through one of our grants. For cryptography-based things, there's I guess 2 or 3 teams that you might be interested in. So one is one of our older teams, which is called the Crypto Team, and that's led by Theo Riffel. And you can find information about him and their team on the blog. I believe there's a place to apply on the blog. You can also go to github.com/openmind/roadmap, and you'll see a big list of all the teams, and you can click into each folder for each team, and you'll have a place where you can apply to join that team. Ones that are doing quite a bit of cryptography at the moment are the Crypto Team, the Differential Privacy Team, so the DP team. Actually, they like to use the word DP because it I think it had several different interpretations. One was like deep privacy, and then also differential privacy. So I think they're intentionally kind of trying to represent both of those. Also, the The security and identity team is doing quite a bit with like self-sovereign identity and zero knowledge proofs and this kind of
Adam,
thing.
right? I
Yeah,
just
Adam
talked to him
Hall. Adam
today.
Hall is great.
I
Yeah,
saw his huge kind of virtual whiteboard, the mind map with all this stuff, and it was mind blowing. So.
Yeah, Adam's quite gifted on putting together really great visualizations for where the roadmap is to be. Which I got to say, if you're working in a distributed team, that's a really nice thing to have in a team leader, for being able to convey kind of vision on paper like that. So yeah, lots of great activity going on. I think those are kind of 3 groups that are pushing pretty hard on cryptography at the moment. There are also some project-based teams that are sort of sprinting on more COVID-specific projects. That are often consuming or have some overlap with these sort of longer-term dev teams. But yeah, if you're looking, hop in. So I see Madeline Mamliano just dropped the link to the roadmap README. Yeah, I highly recommend checking that out. Also, in the high-level README, there is like our kind of 2020 roadmap as well, if you're just curious on where we're going.
Mm-hmm. And Andrew, you mentioned differential privacy a couple of times. So I assume we have a lot of normal machine learning. Sorry for saying normal, but machine learning engineers and data scientists here who might not be familiar with privacy concepts like differential privacy. This, and also if there are any other approaches that you're working now, just let me know.
Yeah, so the place to start talking about what privacy preserving technologies are for and these kinds of tools is first to recognize what the goal of privacy technologies are in general. So I guess maybe my favorite way to start this conversation is sort of to say that that privacy is actually trivial. Like, it's really easy. You just delete all of your data and you have perfect privacy, right? And so everyone has a perfect privacy mechanism built right into their keyboard just for them. But it turns out that's not what actually people want when they say they want privacy, right? Because the truth is, what they really want is they want all the utility from their data without necessarily the risk that it could be spread somewhere else. And so there's this new philosophy that I think is trying to get a bit more at the specifics of what people want with privacy, called structured transparency. And structured transparency separates the privacy problem into 2 parts, which also defines the relationship to how tools like differential privacy are interesting. So sort of part 1 is called sort of the ideal information flow, or optimal information flow, where you're trying to say, okay, given the world, like, who do I want to know what and when? In like a perfect world, if I could do anything with information right now, I could just wave my magic wand and say, you now know this, right? What would I want that information flow to be? And once you specify this, given a perfect world, it's usually quite an eye-opening experience, to the extent that when you go to the doctor, I think this is a really good example. So when you go to the doctor, you might think that the optimal information flow is that I want to spread, like give some information to the doctor, and the doctor goes and talks to the nurse, and then goes and talks to the test result person, and then they confer together, maybe consults another statistician, and then the information flow eventually makes its way back to me, and I learn what step I should take next to be healthy. But this is not the optimal information flow. The optimal information flow is I learn one fact, what I need to do to be healthy. Everything else is an extra thing. It's extra information leakage that most people believe is necessary in order to achieve the final result, which is me learning what I should do to stay healthy. And so once we sort of acknowledge that this is actually the optimal information flow, like, we want some bit of information in my head, the patient, to be combined with some bit of information in the doctor's head, such as medical expertise, this kind of thing, and to compute a function that ultimately just goes back to me. And so then this allows us to shift to phase 2 and say, okay, where does information live now, and what tools are at my disposal to provide the optimal information flow, to not have any other additional information flow other than the one that I want, and to provide a certain level of guarantee around the actual output that I get. Because one of the tricky things that we have when we start hiding parts of the information flow is that it becomes difficult to verify that everyone's bringing the information to the table that you think they are. So, for example, if a doctor is no longer able to see patient records, or in this kind of thing, you're trying to preserve privacy, well, how does the doctor definitely know that they're all there? And how does the doctor know that the patient's actually bringing records that are theirs and that they're bringing all the ones they should, and they're actually listing all the symptoms that they're experiencing and not just the ones that aren't embarrassing, this kind of thing, right? So so when you add privacy, there also ends up being some of these side problems like verification.
And I think SSI kind of comes in, at least from what I understood. Yeah.
Totally. Yeah. So for those of you who are familiar with tools, like there's sort of 3 different groups. There's verification, then there's input privacy and output privacy are kind of like three big groups. So verification is all about saying, okay, are the inputs that everyone's bringing and the outputs that I'm generating sort of all definitely true? Like, are the inputs valid? Are they coming from the people that I think that they're coming from, right? And are the outputs, was the inner computation that I did actually happen, verified computation, this kind of thing, right? So for input verification, often people look at tools like self-sovereign identity and zero-knowledge proofs, which doesn't actually prove to you that the data is what you think that it is, but it does prove to you that an input data is being used in multiple locations. So, and this can be almost as good. So if you're trying to verify that someone's bank account, or someone's actually sending you money from their bank account, a zero-knowledge proof can be useful, not necessarily to prove that the bank account is theirs, but to prove that this is the same bank account that they're using in a bunch of other locations, right? Mm-hmm. So it's sort of grounded in their other historical actions, if that makes sense. So you could do the same thing with the data stream, for example.
So you could say, for example, this health data coming from this person, it's also the same kind of health data that was shared in other places. So that kind of gives you some kind of guarantee that this individual that you don't know who it is not giving you garbage data, or is not giving you your.
Yeah. To the extent that they're also providing the same information at other locations. So like a good example for this is like federated learning. So in federated learning, we want to make it possible for the centralized server to verify that it's getting good data, right? But without actually looking at the data. And that sounds kind of tricky. But one interesting use of zero-knowledge proofs is to at least enforce that each person is giving you the same data over and over and over again, right? That they aren't swapping it out with something else, because this allows you to actually have a more robust learning signal when you're actually watching whether your model is improving or not improving.
We're also not giving you the same thing. That would also be bad.
Yeah, exactly. The other one is, can you verify that, there's not a civil attack happening, right? Where there's 10 different actors that are all anonymous. Make sure that they aren't all. So that's input data verification. Input data privacy are algorithms for encrypted computation. So this is like homomorphic encryption, secure multi-party computation, and functional encryption, and like there's a few other flavors there. And this is just about giving the ability to transform data while it's in a protected state, right? So it's sort of decoupling governance from computation. So normally, whenever you want to compute something, you basically have to give governance to whoever runs the computer, and that is sometimes quite problematic, right? Because you have to always trust the person on the computer. And so when you want to protect the inputs to your computation and also the internal state, I think it's classified as input privacy, but it also includes the internal state to the extent you're training multiple computations together typically. That's what we use encrypted computation for. So we talk about input privacy, verification, and then output privacy is what we use like differential privacy for. So if we have this kind of graph of computation, we got like 2 inputs, data coming in, and then there's like a little computer right here, and then it's producing an output over here, right? Over here we have the question, can I take the output of this computation? Maybe it's what I decrypt from what was homomorphically encrypted, or it's what I publish in some sort of report or make available via an API, something like that. Is it possible to take this output and reverse engineer the inputs, right? So can I take the results of some medical survey or the results of the COVID-19 geography reports and reverse engineer identities, right? So differential privacy is really about how much information leakage is getting disclosed for one or more individuals that's on the input side that could be used to reverse engineer that input. So this kind of ensemble of techniques is designed to make it possible for you to get a very precise information flow so that at the output, you can empower exactly who you want to empower with exactly the information they need to know, and hopefully nothing else, right? And it doesn't mean you don't share information with people. It just means that you get to be a lot more precise about what you do share and with whom.
And so on the output side with differential privacy, does the user data provider, or in this case, it's the patients, or people who are not yet patients, healthy people, do they get to choose how much they want to leak, or that's kind of just a consequence of the pipeline that is used?
Great question. So it depends on how you set it up. So there is another aspect to structured transparency, which is kind of like, where do your consent mechanisms sort of live, right? And the maximal amount of protection, so the maximum amount of consent for individual data participants, is called local differential privacy. And this is where each individual actually adds random noise to their input data before it even goes into the computation graph, like before it even enters the system. This obviously adds a lot more just raw entropy to the whole computation and can affect the output accuracy quite a bit more. However, the benefit is that you get this sort of added protection of privacy. Like, you don't even have to trust the centralized computer. You don't have to trust the consent mechanisms for who has control of the output of the computation. Because your information is sort of already protected. In terms of, but the other flavor, which is output privacy for differential privacy, means that I just now sort of started talking about how differential privacy works. Differential privacy adds noise to data to sort of obfuscate individual points. So before I keep going, I should probably mention an example of this. So an example of input privacy, let's say I'm a participant in a survey and you are conducting a survey to calculate the average age of a large group of people, right? So we could all trust you as a database owner and send you all of our ages, and then you average them up and produce that statistic, okay? But if we wanted to instead do local differential privacy, I might take my age, which is 29, and I would add a random number to it. Let's say a random number between -50 and 50, something that's average. We sample from a distribution with mean 0, right? And so I might send you the number -10, okay? And then you'd take that, and everyone else in the whole population would do the same thing. They would add to their number some random number that has a mean 0 distribution. And so each individual data point wouldn't necessarily convey private information about an individual. My age is clearly not -10. However, you, in expectation, by collecting enough samples, would still be able to, in aggregate, get at the same statistic you were going after, which is what is the average age of this population, right? So that's how local differential privacy works.
What's an example where this kind of adding noise works in real world besides age?
Besides age, so there are various statistics. So differential privacy is almost always about an aggregation over a large number of entities, right? So that's the general setup. So Firefox uses this in its browser for a variety of things. I think it uses it to protect URL autocomplete. I believe it's using autocomplete, and it's also using like background statistics. Also, there's a paper, or actually a report from Apple that says they use this quite extensively in a lot of their sort of operating system level statistics. So they can gather statistics from lots of people that are using devices without necessarily compromising the privacy of any in particular user. So yeah, lots of there are some very large scale.
Right?
What do you say? It can work with location. It's a bit trickier, but it can work with location. And so in that sense, you could think of it like the goal is to reveal a heat map of population density without revealing the exact location of individuals, right? And you want to have some formal upper bound on the possibility that one person could say, look at the output of a traffic app and reverse engineer the journeys of individual cars. If that's a good example.
That's kind of maybe what the MIT Safe Path team meant with blurring.
When they said blur, that's what they meant. Most of the time when people talk about blurring data for the sake of privacy, they are giving an intuitive adjective to describe what differential privacy does, hopefully. Sometimes people say anonymized data, and that usually just means like erasing bits and hoping that it works.
I think anonymizing data doesn't really work to the extent that I haven't even paid attention to it for a long time. I just realized it doesn't work, but that doesn't work.
Yeah, so
most of the cases in news media that they say anonymized data, usually after 3 to 6 months, there's another article. Oh shit!
Yeah, so that's just journalists' future planning, right? No, so yeah, anonymized data is widely known to be ineffective. So I think the most famous case is the Netflix prize. So if you're familiar with, remember the Netflix Grand Challenge, where it's a big machine learning competition where a bunch of machine learning experts competed to build a really great movie recommender. And as a part of this challenge, they published what they thought was an anonymized movie rating data set, where they took the big matrix of ratings that
They
Netflix
removed
has.
a couple of columns.
Yeah, so they replaced all the movie names with numbers, and they replaced all of the user names with numbers, and they're like, great, it's anonymized. There's no PII in it, right? But it turns out that the uniqueness of how you rate movies is actually a kind of signature, right? So that statistical uniqueness can be linked back to individuals if you have some other source to go compare it to. And so within 2 months, some researchers at UT Austin went and scraped IMDb and were able to perform what's called a linkage attack between the data set that Netflix published and the data set that exists on IMDb. So good example of where...
Adam told me about model inversion. This is also this.
Yeah, so same general idea, and so in this case, the statistical result is the model, right? And you're trying to reverse engineer inputs that were in the training data set from the model itself.
So someone could create like a really stupid social app on Facebook that you just like a couple of movies, and if you like, it's like a Tinder interface, you dislike these movies, and then if they have I guess it was probably a Kaggle data, and then they have this like social app results, they could probably figure out who these people are.
So that is one of the approaches, right? So if the other data set is not linked back to wow, that's actually a really compelling use case you just listed. I hadn't really thought about the fact that, like, if you even if you collect,
should we remove this part from the recording?
Yeah, no. I mean, it's important to raise awareness, right? So, like, basically, because people think that when they're publishing seemingly innocuous information about themselves, that they're not revealing anything about themselves. But the truth is that anytime you reveal any kind of unique statistical signal, you're opening yourself up to the potential that someone could use that to figure out who you are and link you to other of your activities. And this is why differential privacy is so important. This is why privacy preserving infrastructure needs to replace a lot of the infrastructure that we have in our own society. And that's the challenge that we have over the next hopefully less than 20 or 30 years, is to try to get it to a robust place where people can maintain control over the only copies of their information while still doing all the same things that they like to do in society.
Okay. So Andrew, before we move to questions and the second part about COVID-19 efforts, is there like an easiest path for machine learning engineers and data scientists who are just getting to know open mind to start their journey and have some level of privacy preserving machine learning in their application?
Yeah, absolutely. So I think that one of the good places, is definitely the best place to learn PySift. Last year we produced, in partnership with Udacity and the PyTorch community and several other guests from great privacy labs, a free course that's on Udacity. So udacity.com/private-AI. I don't know, maybe Madeline would be generous enough to drop that into the comments. But yeah, it's about 6 hours of video with projects and examples for how to do privacy preserving machine learning. So it covers the basics of federated learning, covers a lot of the intuitions and some of the algorithms behind differential privacy, as well as secure multi-party computation. I don't think we've got to cover homomorphic encryption yet, but yeah, I think that's probably the best place to start. It's targeted towards the absolute total noob beginner who has maybe a little bit of Python hacking background. I think that's kind of what we went for. So yeah, okay. Hope you find it helpful.
We could say that's why we don't have a webinar scheduled for tomorrow. You guys go watch Andrew's.
Perfect. That sounds great.
Maybe we just play it here. We just like play tomorrow's webinars. Okay, so let's look at the questions a little bit, if it's okay with you.
Yeah.
So I'll ask this one from Nicholas. In times of crisis like ours now, sorry, do you believe that we give up a certain amount of privacy, or do we make do with the tools available now?
So whether we will or won't give up any privacy is unfortunately not my call. Well, maybe fortunately, I don't know, depends on who you are, I suppose. However, from what I can tell, most of the things that people want to do can be done in a privacy-preserving way. So there are some really awesome algorithms that have been proposed in relatively fast timelines for everything from contact tracing to, calculating statistics for how many people are experiencing symptoms and all these kinds of things that can be done in a perfect or near perfect, if it's okay to use the P word, and that's kind of scary, privacy preserving approach. And I think the real question is whether the actors that have the ability to make these calls can both know that these techniques exist, can access the right talent and also code bases to be able to execute on it, and whether they ultimately choose to, right, and choose to champion privacy preserving techniques. I will be the first to say that there is a certain time delay. Like, it's a lot easier to just, if I looked at contact tracing, for example, and I looked at the amount of development complexity that is involved, lots of people can put together a Firebase app that throws a bunch of GPS locations in the cloud and says when two people overlap. Like, this is not rocket science, right? And that's the kind of thing that a lot of people, I think, could hack together in a weekend. Doing this in a privacy preserving way, I think, is a bit more challenging. It requires a bit more technical chops. And so I do hope that basically the powers that be will be patient enough and will work with the right people to do all the things they want to do in a privacy preserving way. And if they feel pressured to deliver something earlier than those teams accomplish, at least have a roadmap for upgrading to a privacy preserving way, even if they have to make tough choices in a short time. So
I think that's kind of the best case scenario for COVID-a-thon, that we get people from these other weekend hackathons to our 2 months hackathon. and this kind of becomes like a privacy incubator.
Amazing.
And we connect them to people like yourself and other mentors. I think we have at least a few mentors from the Open Mind community. So, and there's also a Discord channel on our Discord server. We're not using Slack, unfortunately, but Open Mind has a really vibrant Slack community. You can also join there and ask them questions. Go to the next one, if you don't mind.
No.
Would you consider MPC to be a larger class set of tools available to compute in the middle? And if the question is clear.
Oh, sorry, say this one more time. I was trying to find where to read it. And
it's questions and answers, the top one. Can you see
I see it.
Yeah.
So would I consider MPC to be a larger class set of tools available to compute in the middle? Yeah. So secure multi-party computation is a it's a class of algorithm that I think if you went to Wikipedia, it would define it as a group of algorithms that allow multiple people to jointly compute a function while keeping all of their inputs secret. So I find that when trying to teach this to sort of machine learning people, that it's a little bit easier to teach secure multi-party computation by saying that secure MPC allows you to share ownership of a number, and then compute over that number while it's in a shared encrypted state, right? So I can take the number 5, for example, and I can split it into 2 shares, a 2 and a 3, and I could give you the 3, and I can hang on to the 2. And this number 5 is sort of encrypted in between us, in the sense that you, by looking at your share, don't know what the number is. Me, by looking at my share, don't know what the number is. And despite this fact that you and I, if we both decide to opt in, can compute with this number. We can perform arithmetic with this number, right? We can multiply it or add it. And if this number is a part of a neural network, we can use it for forward and back propagation, weight updates, and all this kind of stuff. And while we're computing with it, we get 2 properties, right? One, so it's encrypted, it's shared. No one knows what the actual raw value it is. And the second is that we get shared governance, meaning we can't actually decrypt this number or use it for computation unless all the shareholders agree. And so there's a whole group of algorithms that work this way. I find that most of the academic textbooks will think about secure MPC functionally and think of it more like a functional algorithm where it's all about computing a function while keeping your inputs private. But I find that particularly for object-oriented programmers, it's a little bit easier to think about it from the context of shared ownership of a data structure, right? Where no one knows the state of the data structure. Everyone has shares that own a part of the state of the data structure, but you can compute with it while it's in this shared state. And if everyone agrees, you can choose to decrypt it for one or all parties involved.
A new question from my side. So the fact that this is shared is because it comes from multiple parties, and then like you kind of put it together and everyone computes on the whole data.
Say it one more time.
So why is it shared? It's because these different participants contribute different amounts of it, but the computation is done over the whole data, right?
Oh, why is it shared? Yeah, so I guess in the example that I gave, I was the originator of the 5, right? So I think secure MPC is a bit more interesting when multiple different people can create digital assets in the process. So for example, let's say I had a training data set and you had a partially trained model, right? So I could split all of the individual numbers in my data set into 2 shares and send you one of them, right? 2 shares each and send you one of each. And you could do the same thing with your model and send those to me. And then we could continue to train a model while it's in an encrypted state. And all of a sudden, this new digital asset is shared between the 2 of us, right? Because each one of its parameters, each one of the numbers inside the model that is now smarter than any model that someone else had, right, is under our joint control, right? Because neither of us knows the values of the model, despite the fact that together we are able to use it. Does that make sense?
Yeah. I guess this would make a lot of sense in the healthcare scenarios, right?
Yeah, it seems like I mean, there's a lot of different industries that can benefit from more granular access and more granular controls around data and computation. But the most obvious first ones are healthcare and finance, I'd say, and those are the ones that I see leaning into these technologies the earliest.
Okay. So if we could go to the next question, I could also invite some people to screen. If people want to do it, just write in the chat. What are the efficiency and accuracy considerations of privacy-preserving algorithms? That's the first part. And then that is how much extra computation power is needed? What loss of significance could there be in results?
Great question. So with privacy does come a trade-off of either accuracy or performance, or both. And this is true for all the techniques that I said, and the trade-off is different for each of these techniques. So for example, if I were to do differential privacy, and I'm adding, we'll go back to the age example where we're calculating you're going to calculate the age of a group of people, and I'm adding a random number to my own age. If the random number that I add to my own age is only between -1 and 1, right? And so the maximum that I could do is change my age from 29 to 30 or 28. I'm not really getting that much privacy protection from that, right? However, your final result is probably going to be quite a bit more accurate, right? To the extent that people aren't adding as much entropy to the system, and your mean is going to be much closer to the true mean. So a good example. That's a good example of the trade-off between the two. Unfortunately, it's difficult for me to give a one sweeping answer on exactly what those trade-offs are, other than to say that you could summarize. The vast majority, if not all, of the research in privacy-preserving technologies to be focused on improving the trade-off between privacy, performance, and accuracy, right? And so if you think about this as like a 3-dimensional Pareto trade-off, the one of the biggest goals, probably the biggest goal, possibly one of the only goals of privacy enhancing technology research is to push those bounds for specific subproblems. One problem that you might be interested in is deep learning prediction. So I think the fastest encrypted prediction, so either predicting an encrypted model on a data set or running a data model over an encrypted data set, is a 13x slowdown over plain text. This is using a algorithm called SecureNN that was proposed in May of last year. It might have been May of the year before. Yeah, so like 13x slowdown. So it's the kind of thing where, like, in a machine learning context, most things are annoying. Many things are still doable. I would say that for secure MPC, tends to be a bit faster than homomorphic encryption, with the exception of when you're working with phones where your network speed is really low latency. So that's another sort of just generally good guidance. And in many cases, the best trade-off between performance and accuracy and performance, accuracy, and privacy is some ensemble of these techniques, which is one of the reasons why we want to basically bake them into easy-to-use tools so you can sort of turn the knobs and tune them relatively easily to be the optimal for your particular use case, right? Because I mean, like how it's optimal can even change just based on network latency. Like if someone's phone switches from Wi-Fi to being not Wi-Fi, all of a sudden the optimal calibration might be different, right? Just because you're operating under different constraints. So hope that's helpful. I can't answer that question too directly, but maybe that gives you a bit of a feel for the problem.
So it's kind of between 10 and 1,000 times slower.
yeah, or worse. I mean, it depends on the task again.
Okay.
Yeah, it depends wildly on the task, but yeah.
Got it. But I think in a lot of COVID-related applications, like you could compromise on speed because like humans do not move so fast. Like you could do it on historical data, and even if it takes like a week to compute, but you don't sacrifice anyone's privacy, and then you get the best accuracy, that could be okay.
Totally. And the other thing with a lot of contact tracing apps is that comparing, say, one person's measured location with the location of a patient is a naively parallelizable thing. So if at that point it just becomes a matter of how much how big of a compute bill can you afford, because if it takes 2 seconds to compare any two GPS points using private set intersection, then in theory you can do all of them in 2 seconds if you have enough compute available to you in the cloud, if that makes sense. So yeah, I guess financial cost often is the other thing that you're trading off in this scenario.
Got it. So we have a couple more questions, but maybe we can start talking about specific COVID-19 related efforts at OpenMind. I think you have these 2 blog posts. I don't know if someone, Madeline or Robin, someone could share those 2 blog posts.
If you go to openmind.org as well, there's a link to both the blog posts that comes up in a
okay, it's a call to action.
Yeah, so OpenMind, we, like many other projects, jumped in the very beginning, prototyping a contact tracing app just to see sort of what it would be like and potentially that it would be useful. It became very clear to us relatively early on that there's going to be a lot of people building a lot of apps in a lot of different jurisdictions. And in particular, nearly every government around the world is all trying to respond to this in parallel. And so there's kind of a big routing issue going on right now that's difficult, where you have thousands of groups all working to solve problems all at the same time. And some people are making really good progress on problems in some areas and some are not. And so one of the big roles that we're trying to facilitate is just helping people who solve problems to sort of spread their ideas to everyone else so that we can all benefit. And the other big group of things that we're doing is helping to provide resources for teams that lack privacy expertise. Because as I mentioned before, I think the ratio of people who know how to deliver web apps relative to people who know about privacy enhancing technologies is sort of like 1 billion to 1. I mean, it's like, privacy enhancing technologies are still very early, not very well known in a lot of cases, and there's a lot of teams that need to build something really, really quickly. So for repeatable use cases that need some sort of privacy enhancing technology, where there isn't already an open source component being built somewhere in a library form, we are also pushing forward on several internal projects to build individual components that people will need inside of their apps. So basically, this means we're not focusing on building our own apps. We're focusing on just consulting on everyone else's apps, trying to make sure that they're privacy preserving. And we do that by either education, so spreading ideas around and helping everyone know about what the best solutions that are being talked about are, or building open source components that no one has yet got around to making mature. And so for us, there are 4 components or 4 projects that we're working on that we think are sort of the highest value, and that they're also sort of the most underrepresented in other projects that we've seen, or at least they were, when we started the projects. Obviously, the the space is changing really rapidly. So one of the projects, and please do jump into any of these if you are interested in helping with COVID-19 response.
There are links on your blog post that go directly to the Slack channel, right?
That's right. That's right. So and actually, there was in the Slack channel, there was an announcement that went out today that had links to all the different sub channels inside of the Slack team that make it so you can get involved in these projects. So one of them is differential privacy focus. So many of you might know who are cryptographers that like there's the algorithm and then there's a really good trusted implementation of that algorithm, and often those two things can be very different. So in the context of differential privacy, because it's so new, there's differential privacy, the idea, and then there's, wow, do we have like a truly vetted, security audited differential privacy implementation that we can really trust? And I believe it was sometime last year, Google released their differential privacy C++ library that they've used in a wide variety of implementations, which for us as a cryptography community is a huge deal, right? Because it means that this thing has been battle hardened, has been worked on by some of the world's top cryptographers. But one of the challenges is that deploying C++ inside of your mobile app or your Node.js server is annoying to say the least, and a blocker for some projects who might not be familiar with that. So one of the projects that we're pushing on really quickly is actually just to wrap that C++ library in all the languages that people are building apps in, so that it can be made available for differential privacy as people need it. So please do jump on that project.
And I can say, if you use this for your COVID submissions, you get an extra point.
Awesome, perfect, yeah. And so definitely jump into the Slack team that's jumping into that project, and I'm sure they'd be super keen. That project is also being managed by Ben, who's in Australia as well. So it's one of our few projects where the team lead is actually on the opposite side of the world as well. So if you're looking for someone who's sort of in your time zone and that time zone is not compatible with the GMT, it's a great project to participate in. One of the other projects that's really fantastic is private set intersection, like I mentioned before, which is it's similar in flavor to differential privacy in that it's about taking private set intersection and making it available on all platforms using really robust implementations that already exist, right?
Including mobile, right?
Yes, including mobile, actually, and especially mobile, to be honest. So the idea there is that there's a whole group of COVID apps that are doing one or more flavors of comparing data on the phone with comparing data that's in a server, and doing that without having to download data from the server or send all the data to the server requires something like private set intersection. So trying to make that as widely available and easy to use as possible is a big part of that project.
Wait, does this also require the server side to be compliant with this? Do they also need to re-implement? Mm-hmm. Oh, okay.
So I mean, we're supplying both server side and client side libraries that talk to each other. So and that's another big part of it. Is like for some of these, there were like partial implementations that worked in one language, but there wasn't the serialization and deserialization logic to cause them to be able to be used together. Like so that you could serialize an encrypted message in JavaScript and send it to your Python server running Flask, and you could actually decrypt it and work with it, right? To complete the private set intersection protocol.
Mm-hmm. So what's number 3? You said there are 4.
Yeah. So actually, and to be honest, there are also more than 4, and it depends on how many slices of these projects you're going to work on. So each of these projects have individual sub projects. So for everyone who's listening, if I don't call out your project by name, please don't get mad at me. But please try to route people as needed based on where effort can be most helpful. So another one of the projects is around mobile data scraping. So in a lot of cases, people have notional control over their own personal data, but usually it's sitting in some database somewhere. And often they need the ability to be able to pull it down to their own device, right? So you could imagine one of the most important use cases for this is enabling contact tracing employees who are actually doing sort of like, standard real like epidemiological, not the contact tracing apps. I mean like contact tracing the sort of the medical exercise. And a patient wants to be able to remember every place they went for the last 2 weeks. Well, as it turns out, when they were going these different places, they were leaving a data trail everywhere they went. And so if you can make it possible for them to sort of pull down all of the breadcrumbs they left along, whether
and
that's
their
from a variety of different sources. Yes. I don't know if that's one of the projects that people are working on, but
Okay, that's a hackathon project.
is it? Um, but yeah, so the idea here is to make it easy for people to access their own data, right? By being able to pull it down to their own devices, and that's a massive effort from the context that, like, you know, if I wanted to be able to construct the full profile of everywhere that I've been using all of my sort of digital footprints, I mean, there's a lot of different sources that I would want to be able to pull in, because you don't want to miss anything, right? You want to make sure that, no, oh yeah, that's right, I went to the gas station or wherever else, right? And it can be difficult to remember, when you're in the midst of a stressful situation, where you were, 1-2 weeks ago.
So I wanted to also ask you, like, maybe the last part for a couple of questions, ideas for people to start working on as like end user applications. And here, for example, this could be used for this like very recurring idea of like, have I maybe been in contact with people that have our patients, or maybe there are heat maps of hot zones that are generated later, so you could kind of go back and compare if during those, like, periods of very hotness in those areas, you've also been there.
Yeah, so these techniques could be used for that kind of thing. I would say, please be very, very careful with doing heat maps. So as you're familiar, I think a lot of people are doing projects with heat maps right now. But again, getting back to what we talked about before with structured transparency, like the goal is not to transfer information to users about everywhere that every patient has ever been, right? The goal is for me to ultimately, learn what should I be doing in my own life to keep myself safe. And so releasing a heat map is actually releasing a lot more information than is necessary for me to be able to learn whether I'm staying safe, whether I can go to specific locations and this kind of thing. So do try to be creative in the ways that you preserve privacy, and really utilize the full set of tools to make it so that people can get after that end use case, which is actually much more narrow information transfer than, say, I think a heat map would be dispersing by default.
So here was an idea that I think we had a couple of days ago, in line with structured transparency. So imagine when you want to go somewhere, you leave your kind of self-isolation, and you would only get the data with some blaring around the path that you will travel, not the whole heat map of the whole city. You would only get, so if anyone wants to build this, I would definitely also support it. So you use Google Maps or OpenStreetMaps, and then it just shows you on your path and by public transport what's the risk. And maybe it could even, that would be cool for Google to implement, to even offer you alternative routes if you're going through some like super hot zone. Maybe there was like a protest or something.
So I think when a few weeks ago, that was one of the lines of thought that a lot of people were on. One thing that's worth considering also is that it seems to be that people are contracting the disease more from person-to-person exposure, as in you happen to be standing next to each other, than, say, touching similar surfaces. So the notion of hot zones is it might be a little bit oversold. I mean, yes, you'll have a larger number of people that are around who have it. So like in that sense, I guess it's kind of a hot zone. But also, I think it's important to recognize that the primary transfer mechanism, best I can tell, and I'm not an epidemiologist, so please don't take my word for it. But from what I've read, it seems like people believe that most transfers are happening as a result of people standing next to each other for a few minutes and breathing on each other and that kind of thing.
That makes sense. Okay, got it. Yeah. So then don't spend too much time. And the last one of the 4 main lines of effort.
Oh, yeah. So there's a really big push going on self-sovereign identity. So for those of you who aren't familiar with self-sovereign identity, the idea is very akin to someone signing a piece of paper making a claim about you, right? So let's say that we'll talk about it in like a not COVID related case, just to explain what self-sovereign identity is all about. For let's say I want to go into a club, right? And if I'm in England, I need to prove I'm 18. If I'm in America, I need to prove that I'm 21. Normally, you go up to the bouncer at the door, and what does he need to know? So this gets back to structured transparency again, right? The bouncer needs to know am I older than a certain threshold, right? Bouncer doesn't even need to know my true age, doesn't need to know who I am, doesn't need to know any of these things, right? The true information we're trying to transfer is I'm old enough to consume alcohol in the jurisdiction that I'm in. However, the thing that we do is we hand over a copy of our driver's license or our ID, right? And they learn our first name and our last name, our date of birth, driver's license number, state we come from, home address, usually what our signature looks like, all the different, attributes like brown hair, 6'1". I mean, I guess they can see that in your person looking at you, but we transfer a whole lot more information than what we're actually is needed for him to verify something about my identity, right? And so self-sovereign identity really builds on this idea that your identity is actually composed of lots of very specific claims and very specific attributes of yourself. And what we really want to be able to do is have a society where when I need to verify my identity, it's usually not everything about my identity. It's usually a very specific thing, right? One really common one is I need to verify that I'm unique and that I'm not one of the other users in your database, right? So if you're familiar with Sybil attacks, or maybe I need to verify that I'm above a certain age, or maybe I need to verify that I've passed a certain medical test, right? Or that I've passed a certain academic test, like all these kinds of things. And so in the real world, when we want to do this very specific kind of claim, what we'll do is we'll issue, a certificate, and someone will sign it, right? And they'll say, all right, I'm Dr. So-and-so, and I authorize you to get this certain drug from the pharmacy, right? And I can take the certificate and I can walk up to the pharmacy and then they'll give it to me, right? But there's a few problems with this notion of a certificate. So even though it's inherently more privacy preserving, I don't necessarily have to prove to the pharmacist, that I'm sick or that like all these other things. I just have to show them a certificate and they're gonna give me what the medication that I need. But signatures, they're not that great, right? They're hard to verify. Like, is this person really that familiar with Dr. So-and-so's exact signature? Like, would they know a fake one if they saw it? Two, it's easy to forge, right? I could trace over it, or I could just scribble something that looks kind of like a doctor's signature, which never looks like their name anyways, right? And it's also very difficult for the doctor to revoke later. So like maybe the doctor later realizes, oh no, this drug is no longer any good. I need to stop all the prescriptions that I wrote. Like, no, it's just a piece of ink on paper. You can't sort of unwrite it later. So what self-sovereign identity allows you to do is basically store all of the attributes of yourself in the form of a bunch of certificates by other people who claim certain things about you, right? They might claim that you have a certain test or claim whatever, but instead of a written signature, it's a cryptographic signature, right? And this cryptographic signature is formed in such a way that someone else can verify it, despite the fact that they can't issue it, right? Mm-hmm. So the pharmacist could verify that the doctor has cryptographically signed my thing and that signature is still valid, that it hasn't been invalidated somewhere, right? Even though and I can't forge it, right? It's a single time use key, right? It can only be used for this one particular thing. So yeah, this is kind of the area of what self-sovereign identity is about. It's a lot like privacy preserving machine learning, the extent we talked about a second ago, where it's all about facilitating a very specific information transfer, right? But in this particular case, it's about facilitating it. Facilitating a certain kind of information, which is a claim by one person about another person, right? So it's some entity is making a claim about me, and what this proof is basically saying is that like only that person could have actually made this claim, and the fact that I have it, and that it matches my matches my hash, matches my private key, this kind of thing, right? That it's definitely about me, and so in the context of COVID. There's lots of really interesting applications of this, especially in the realm of proof of health and like what happens. So I think the UK government just announced that they're going to do immunity passports, right? And so the immunity passport concept is, if you have already had the disease and you take some test that says that you have antibodies, right? then you want the ability to prove to other individuals that you're safe to go back to work, that you're safe to prepare food, that you're safe to be around other people, you're safe to do all these other things, right? You're a safe member of society because you've already had the disease, and in theory, it's very unlikely you would transfer it to someone else. And so this is the claim, and this is something that could be done with a piece of paper, right? But and an actual physical signature. But this is sort of going to be prone to a lot of the same things we talked about a second ago. But self-sovereign identity offers sort of just an extra layer of protection and verification around issuing these incredibly valuable certificates, to the extent that there's the potential that this identity, or sorry, this immunity passport could allow people to have access to a non-trivial number of things, and so you want to make sure that it's right, and that it's hard to forge, and that it's grounded, and that it's verifiable. So that's one of the use cases of interesting self-sovereign identity. But really, self-sovereign identity is all about verifying any attribute about a person according to another person, right? That's sort of how I think about it. Now, all that being said, I'm actually not that deep of an expert in self-sovereign identity. I spent a lot more time in machine learning than I have in self-sovereign identity, but I think it's a super important tool, and there's a team working on making that type of scalable infrastructure really accessible. So I hope.
Yeah, I saw the plans today, so I think in a few days your team is going to publish more.
Yeah. So I guess for all these things, there's two big efforts, right? One is all the project management, like what are we going to build and how is it going to work? And then there's the go, let's get it done, right? And each one of these projects are in different phases, and often even iterative phases of what are we going to build and go. So so yeah, if you hop into a channel and it's quiet for a weekend or quiet for a couple of days, don't fret. It just means people are processing new information in a highly dynamic environment and trying to make sure that whatever we end up producing is useful to as many projects as possible.
Okay, Andrew. As the last question, I want to hear, do you have any ideas for projects that teams could start working on that are feasible within 2 months to get to somewhere meaningful? Things that you want to see maybe already working on at OpenMind.
Yeah, so one thing I would encourage people to do, and this is, I am very sympathetic to why some folks wouldn't want to do this, but I would really encourage people to build open source components for specific subproblems. And to really join these initiatives as some of those subproblems that are really useful. But there's other problems in the area that are as well too. Like notice, I haven't mentioned Bluetooth contact tracing, Bluetooth-based, like peer-to-peer based contact tracing. So one of the outstanding problems there that I haven't seen really verified is we need to figure out how to, with a very high degree of confidence, calculate how far two phones are from each other, right? Because this matters, right? So like one cool project is check out the Google Nearby API. So it's able to allow two phones to talk to each other, not just via Bluetooth, but also via ultrasonic sound and by Wi-Fi. And if you could use some combination of this Google Nearby API to get as accurate an estimate as possible of the distance between these two phones, that component by itself, right? By itself is going to be so useful to so many different apps that are being deployed in so many different jurisdictions, right? Because so many apps are trying to make a claim that someone has or hasn't been exposed based on their proximity and the length that they were within someone's proximity, right? So yes, you can go and build your own end-to-end app and try to pitch it, and that's great, and there's lots of teams doing that. But I would say that if you want to maximize for impact and you want to really maximize for making the world better, pick one of these hard specific problems and go deep and just nail that specific problem. Because there's thousands of apps around the world. And even if you could get one government to adopt your app, that's not nearly as impactful as if you're able to build a component that 100 different apps all around the world all choose to adopt that makes all of them just a little bit better. Especially if you're not sort of connected within local government jurisdictions, which is a big part of how things get adopted in short time frames like this. So I would highly encourage you, please do everything in the open source. contribute everything back to the community, make it accessible to as many apps as possible, meaning don't be competitive. Like if someone else starts to land a deal, like jump on board, try to be as helpful as possible. Blog, like write about everything that you're doing, write about everything you're thinking about, write about, you know, all the solutions that you think people might not be considering, facilitate the transfer of information, and just be as generous and open as possible with your time. And don't get frustrated if don't get frustrated if you find yourself on a project and then learn that someone else is a little bit farther along, right? Just pivot and jump, right? Just keep going. Like this is not a startup space. This is not a time to be focusing on like, you know, VC competitiveness, you know, startup this, startup that. Like this is a time for all of us to work together to ultimately land on the best solution and the most secure protocol for the most privacy preserving sort of infrastructure that's possible. So yeah.
Maybe Open Minds should sponsor a prize for that.
Yeah, we can look into it.
Yeah. But I would encourage our developers to exactly follow this approach. And one thing that we're doing at COVIDathon is we're using a tool called SourceCred that actually rewards people for being collaborative. It measures how much maybe you can run it on Slack. I don't think it's available yet. It's sourcecred.org. And it goes through all the Discord messages and GitHub libraries, and it looks at like how it's based on Google's PageRank algorithm, like a modified version of that. And
cool.
Yeah, so we're distributing prizes based on how collaborative you are. So if you create a library that's being used and starred by like thousands of people, that's amazing. You definitely win not just a prize, but also you'll get like much more adoption.
Fantastic.
That was the best, I guess, way to end this. Thanks to you, Andrew, for staying with us also a bit longer than 1 hour. And thanks to everyone for joining this webinar. You can go to Open Minds community and also join us on DevPost. By the way, Andrew, if people work with you on your project, it's okay to also submit them to our hackathon and others, right?
Sure. Yeah. Of course. Yeah. Please do. Oh yeah, and one more thing I wanted to flag, just to mention it. Look up Apple's Find My algorithm. There's a great Wired article. So Google like Find My and then Wired. I don't know if someone wants to drop the link into the chat. It's a really cool privacy preserving algorithm that's very relevant for contact tracing. More than we should probably get into at the moment, but like it is a really well written Wired article, and really I think opens your eyes to just how privacy preserving some of these contact tracing apps can be. So yeah, definitely check out that algorithm. It's very cool.
Okay, thank you. So thanks for everyone for joining us, and see you during the hackathon. Bye, Andrew.
See you in the hackathon. Bye.
Bye.